Welcome to the webinar, Open Inventor 3D Software Development Toolkit for Medical Applications. This is a short introduction to some of the powerful features that the Open Inventor 3D Toolkit provides for developing both medical and general life science applications. It's not our intent to give a programming course. The overall goal is for you to leave this presentation knowing what the Open Inventor product is, the value it brings in features, productivity, performance, and quality, and how we can help you to create or improve medical visualization programs. Here's an overview of what we'll be talking about today. First, an overview of Open Inventor concepts and features. A quick look at what coding with Open Inventor looks like. Then on to demonstrations of some medical applications and workflows that Open Inventor enables. First, a few words about who we are and how we serve our customers. The FEI Visualization Sciences Group develops 3D visualization software both for programmers developing 3D applications and for engineers and scientists who need data visualization and analysis tools. Today, we'll be talking about our software for application developers. We use it ourselves to develop our application products. And we have hundreds of customers worldwide, both commercial developers in medical, oil and gas, design and engineering markets, and major scientific, research, and government organizations. Founded in 1980, our team is composed of uniquely experienced and strongly committed people who are both deeply knowledgeable about 3D visualization and passionate about providing the best technology and the best service possible. We serve our customers worldwide through R&D, sales, and operations offices in the United States, France, Germany, and the United Kingdom, as well as through our dedicated distributor channel. Now let's get started learning about Open Inventor. Open Inventor is a software development toolkit, or SDK, for 3D visualization applications. As you can see here, an amazing range of medical applications are built with Open Inventor. They include virtual simulation, computer-based training, 3D reconstruction, and interactive visualization software such as digital autopsy software. One aspect of Open Inventor is an object-oriented productivity toolkit that allows your developers to take advantage of the raw performance of OpenGL, the industry-standard graphics hardware interface, but without having to do tedious, error-prone, low-level programming. This allows your developers to focus on their real added value, domain-specific expertise. In fact, Open Inventor is much more than this. Open Inventor provides a high-level framework called the scene graph for defining the objects and attributes in the 3D scene. It provides a 3D rendering engine with very high performance and state-of-the-art algorithms for maximum image quality. It also provides an extensive set of built-in components for managing your data, viewing, and directly interacting with the 3D scene. Open Inventor is a perfect solution for rapid application prototyping, both because you work at a higher level than OpenGL, and because many operations that 3D developers typically implement, like moving the camera or selecting and modifying objects, are already implemented for you. But in fact, Open Inventor provides much more than this. In addition to the core feature set, we've also built extensions that add the additional features needed for specific kinds of data and for specific markets. They actually extend the set of objects, data types, and rendering techniques that are pre-built for you. Let's quickly take a look at what extensions provide for medical and life science applications. The Volume Viz extension is a full-featured toolkit for managing and visualizing image and volume data, whether it's a stack of images from a CT scan, an MRI, an electron microscope, or any other kind of image acquisition system. Volume Viz allows for interactive navigation with very large data sets and even multiple data sets, even when they cannot be loaded in memory. We'll be seeing a lot more of Volume Viz in this presentation. The MeshViz extension adds support for managing and visualizing surface and volume mesh data. This is valuable, for example, in finite element analysis or computational fluid dynamics. It also brings an extensive collection of charting objects. The hard copy extension allows applications to export a 3D scene for embedding in a PDF file using the standard Adobe PDF 3D technology. Hard copy also supports rendering to vector formats, including CGM, HPGL, PostScript, and GDI extended metafile. Core Open Inventor itself supports rendering to arbitrarily large images for publications and posters. Open Inventor also provides a general triangle export tool that can be used, for example, to generate STL files for 3D printing. The ImageViz extension provides advanced 2D and 3D image processing and analysis capabilities for medical imaging software applications. These capabilities cover the whole application workflow, from image filtering and pre-processing through segmentation and data analysis. The Remote Viz extension enables you to add server-based 3D interaction and visualization into web-based applications that can display on any device with an HTML5-enabled web browser. Let's talk about some concepts and architecture of the toolkit. Open Inventor is an object-oriented 3D toolkit built on top of OpenGL and can be used with the C++, Java, or C# programming languages. Each Open Inventor object manages its own state and, for example, renders itself if it's a shape. The programmer doesn't have to implement rendering calls, just build a tree of these objects called the scene graph that describes what the 3D scene should look like. We call these objects nodes. You can see a simple example of a scene graph here, and some of the kinds of nodes you will use to build the scene graph. Hierarchy and inheritance of properties in the scene graph makes it easy to have multiple shape nodes render from the same data, for example, a volume data set, but also easy to apply different properties, for example, a color map to each shape. In summary, your application will be responsible for defining the appearance and the meaning of the 3D objects in the scene. This is the most important part, where you use your domain-specific knowledge to create value for your customers. Open Inventor will be responsible for rendering an image of those objects, maximizing performance and image quality, and ensuring that complex scenes are rendered correctly. Next, we'll look at some data management concepts for volume data, and then a simple medical rendering program built using Open Inventor. To quickly develop a prototype application for rendering a medical dataset, we will use Open Inventor's Volume Viz extension. Volume Viz provides both data management and rich interactive visualization of complex volume datasets. Different representations include volume rendering, axial and arbitrary slices, isosurfaces, and embedded 3D geometry. These can all be combined into a single Open Inventor-based application. The Volume Viz solution includes a hierarchical multi-resolution large data manager called LDM. This technology allows rendering of very large datasets and multiple datasets with reliable interactive navigation, even on machines with limited performance and memory. You can see an example here, how LDM manages the most relevant tiles of data in main memory and GPU memory for the current visualization. Volume Viz LDM is used in many commercial applications today and has been stress tested on hundreds of gigabytes of data. It is designed to support up to terabytes of data. Here is the complete code for a very basic Hello Slice C++ program. To get an image on screen and start interacting with it, only a few steps are needed. First, initialize Open Inventor and its extensions, here Volume Viz. Next, create the scene graph objects. Here we create a volume data node that loads data from a disk file. If possible, Volume Viz automatically selects the appropriate volume reader. Naturally, it includes an advanced DICOM reader. We create a transfer function node using a predefined color map and we create a shape node that renders an axis-aligned slice. Next, assemble the nodes into a simple scene graph, similar to the one we saw earlier. Then, create an Open Inventor viewer and give it the root of the scene graph. In this case, the viewer will notice that the application did not create a camera or a light node and automatically add those above the application scene graph. Finally, we display the window and start the event loop. The viewer automatically handles mouse events, allowing the user to pan, zoom, and rotate the scene we've created. This is all it takes to get an interactive 3D scene on screen. Now that we've seen a basic medical slice example, let's run another Volume Viz program showing full volume rendering of a relatively large DICOM dataset. We've pre-selected a default data range and transfer function for this dataset. We have also enabled lighting and some high-quality rendering options like cubic interpolation. First, we'll show the built-in viewer functionality for rotating, panning, and zooming the camera. We'll zoom on one part of the data, then pan across to a more interesting part. We can also interactively rotate the view. Notice that the rendering quality automatically changes when we begin moving the camera. This is one of the features that allows us to maintain interactivity even for large data and high-quality rendering. Now I'd like to introduce another powerful Open Inventor tool, the IV-Tune Real-Time Scene Graph Editor. This is a built-in Open Inventor component and can be activated at any time by pressing the Shift F12 shortcut. It actually opens in its own separate window, so I can still see my 3D scene, but I've focused the video recording on the IV-Tune window temporarily. When we expand the tree, you can see the structure of the scene graph is still quite simple even for this quality rendering. Here's our camera, the data node, the transfer function, the data range, the rendering options, and the actual volume rendering node. By showing you the structure of the scene graph, IV-Tune can help you debug your application. If we click on one of the nodes, for example the data range, IV-Tune will display the fields of that node and allow us to interactively modify them. This makes it easy to experiment with the many rendering options. Let's go into the volume rendering options and enable ambient occlusion. This is an approximation of global illumination in the scene and can be very helpful to visually differentiate the various structures in the volume. I'll switch back to the rendering window so you can see the effect. This is just one of the many image enhancement effects available in Volume Viz, including edge enhancement, 2D edge detection, and boundary opacity enhancement. Now let's look at some more advanced applications using Open Inventor. An important feature of Open Inventor is that it scales from high-end graphics workstations down to laptop machines. The videos you see in this presentation are running at actual speed and were generated on the hardware shown here. Here we're going to show min, max, and average intensity projection along with slab rendering. On the left is a 3D volume rendering of the dataset that shows us visually the position, orientation, and thickness of the slab that is being rendered in the right-hand window. The red arrow in the center shows the direction of projection. The lines, cubes, and spheres you see are part of a 3D interaction gadget in Open Inventor called a manipulator. This one allows us to directly manipulate a 3D box, which could be a region of interest, or in this case a slab. But first, we'll grab a rotation handle on the manipulator and change the direction of projection. We're using average intensity projection right now. Next, we'll grab a scaling handle on the manipulator and change the thickness of the slab. If we rotate the slab again, you can see the current thickness of the slab and the corresponding image on the right as the direction of projection changes. We can also grab the slab and move it through the volume. in any direction we wish to orient it to. Next, we'll switch to minimum intensity and then to maximum intensity projection. Let's rotate the direction of projection again so we can see what that looks like with the maximum intensity projection. And again, we'll move the slab through the volume. And finally, change the thickness of the slab. Next, we'll look at a typical 4-view medical application. This is a demonstration program based on Open Inventor, Volume Viz, and the Qt User Interface Toolkit. First, we select the list of DICOM files that we want to load. We'll get 4 windows, one with 3D volume rendering using GPU raycasting to get high-quality rendering with high performance, and 3 others for 2D rendering of the left, sagittal, and posterior views. Just by changing the minimum and maximum values of the data range, we can extract a new rendering. You'll also notice that the resolution increases with time as LDM loads the full resolution data. Now we can click on the volume, and the picking mechanism built into Open Inventor will tell us the position of the cursor in the volume. We'll use that information to update the positions of the corresponding 2D slices. Likewise, we can click on a 2D slice, get the cursor position in the 3D volume. We'll use that information in a similar way to update the other 2 2D slices. The picking mechanism can also tell us the value of the voxel that we're pointing to on a slice or a volume. Volume Viz provides features to manage the transfer function. Here we're selecting some of the predefined color maps embedded in the product. Of course, you can load your own color maps and create color maps programmatically. Here we're handling input events so that dragging the mouse horizontally and vertically modifies the min and max values of the color map. In an intensity or grayscale color map, we could use this to change the window level or contrast and brightness. Next, we'll do the same thing in the 3D view. Using GPU rendering, modifying the transfer function is fast and interactive. We've already seen one example of a manipulator 3D gadget. This is the built-in region of interest manipulator that allows you to clip the volume along its major axes. This is very useful to see details in the dataset and to select hidden parts. Note that this is a fully interactive clipping operation, not actually cropping the volume. If there's not enough memory to load the entire volume at full resolution, Volume Viz will automatically increase the resolution as the region of interest gets smaller. In addition to lighting and material properties, Volume Viz also supports a variety of image enhancement techniques, including shadow rendering. Voxels that are at least partially opaque can cast shadows on other voxels and on geometry in the scene. Shadows can help the user perceive the shape and spatial relationships of structures inside the volume. In addition to combining multiple volumes, it is also possible to combine volume and geometry rendering. Let's import a previously extracted isosurface representing the bones of the skull. Now, by changing the minimum and maximum values for the data range, we can change the rendering and see the skin. Again, by using the region of interest manipulator, you can clip the volume rendering. this volume clipping does not affect the geometry, although there are separate clipping operators that we could apply to the geometry. And finally, the DICOM reader allows you to extract and use all the metadata contained in the DICOM data file. Next, we'll look at some workflows, starting with segmentation of the volume data. With the features provided by Open Inventor and its extensions, we can implement, for example, a workflow that starts with a stack of images, includes segmentation, and extraction of surface geometry, and finishes with export to a PDF file with an embedded 3D scene. In this demonstration, we'll show a 3D segmentation technique that is independent of the voxel values and only depends on their position in the volume. We call it freehand sculpting. First, we rotate the volume to the desired view direction, normally one of the major axes. Suppose you want to extract a specific region in the body. Here we'll extract the heart using a freehand lasso. The lasso tool allows you to draw a 2D polygon on the screen. We'll use another built-in tool to extrude that shape into the scene, creating a 3D polygonal shape that we can use to clip the volume. Next, we'll rotate the volume to another axis and draw another polygon. We'll extrude that to create a second polygonal shape. Open Inventor also includes a tool that combines multiple 3D shapes by union or intersection. Here, we intersect the two shapes to create a clipping region that further isolates the structure of interest. But perhaps we clipped a little too much in this case. We'll draw another polygon and add it to the clipping region to restore the missing piece. Now we'll rotate to the third axis and lasso several more regions that we want to remove from the final volume. Using a GPU-based technique, Volume Viz can rapidly display one or more surfaces corresponding to ISO values in the dataset. This technique is quite interactive, so we can use it to interactively explore a dataset, or, in this case, to visually select the optimal ISO value. Then we can use the Mesh Viz extension to extract the actual geometry of the ISO surface as a triangle mesh. We can export the triangle mesh as a set of triangles, for example in STL format for 3D printing, or as a 3D scene that can be embedded in a standard PDF file. The free Adobe Acrobat Reader has a built-in 3D viewer that allows the recipient of the document to interactively view the exported geometry and select portions of it. Here we'll use the new Image Viz extension to algorithmically segment each vertebra of a spine. This is video of the actual program running, but we've edited out some of the less interesting steps. We have two inputs, the original dataset, a stack of images, and a set of markers that we created in a second volume. In most cases, spines are similar for similar-sized subjects, so we could load a set of predefined markers and adjust their position by hand or automatically. When the markers are well positioned, we use the original volume dataset and the marker dataset as inputs to the Watershed operator. The output of this operator is a new label volume dataset with a unique integer label value assigned to all the voxels that belong to each of the vertebrae. Next, we'll look at an example using custom shaders provided by the application. Volume Viz allows the application to override or replace specific steps in the volume rendering pipeline. by supplying a custom shader function written in GLSL. For example, the application could provide its own algorithm to compute the color or gradient of a voxel, to combine values from multiple volumes, or, in this case, to shift the position of each voxel to simulate cutting through a volume. Next, we'll look at how to provide 3D rendering as a web service, allowing your application to display in the user's web browser on almost any screen, including mobile devices. Open Inventor's Remote Viz extension brings the same cutting-edge 3D visualization and rich interaction capabilities to web-based applications, providing a high level of interactivity and visual performance on any display device, including tablets, phones, laptops, or workstations. Remote Viz allows all your users to interact in real time with very large 3D datasets and security-restricted datasets. There's no need to transfer data to the client device because the data access, computing, and 3D rendering are performed on the server by the Open Inventor Remote Viz service. Both Open Inventor and the Remote Viz service are available for a wide range of server machines. Remote Viz-enabled applications can be hosted on standard virtual machines from providers such as Amazon Web Services. The Remote Viz service allows multiple users and flexible collaboration. A client can connect to the service and initiate a new session or connect to an existing session. In the latter case, rendering and interaction are shared between all clients connected to that particular session. Open Inventor allows easy integration of multi-touch gestures such as tap, drag, and pinch into a 3D visualization application. The Remote Viz service transports gestures back to the server, providing an easier, more comfortable, and more intuitive way of interacting with 3D data. Everything you know about developing 3D visualizations using Open Inventor is now directly applicable to developing 3D web-based applications. If you have an existing Open Inventor application, your existing code to create and modify the scene graph can easily be ported to the server environment. We've reached the end of our webinar. I hope you found it informative. In this slide, you can see a few examples of the many medical applications that are based on our toolkit. You can also read our customers' testimonials on our website. This short presentation can only scratch the surface of the many features provided by Open Inventor and its extensions. You can find more information about these features in the Open Inventor documentation and download a trial use version to try it out. If there is anything we haven't covered, please ask us how Open Inventor can address the 3D visualization requirements of your next application. Thank you for watching.